Okay, welcome everyone to session 3C, Massive Black Holes 2. Our first speaker is a remote presentation. Whenever you're ready, please go ahead and share those slides, and we will get started momentarily. Right, so our first speaker will be Rahul Srinivasan, who will be telling us about low latency alerts of massive black holes with binaries, or with Lisa. Sorry.
Perfect. Thank you. I'll be sure to keep it short. I know we have a lot of talks going on here. Hi, everybody. I'm Rahul Srinivasan. I'd love to have been there, but unfortunately, due to visa issues and passports, I'm not able to be there. But yes, I'm a postdoc in CISA. I have a few of my colleagues there as well. If you have any questions and I'm not able to answer them, you should ask Lorenzo Copperoni, a PhD, a soon-to-defend PhD student in the audience, I hope. Right, so I am talking about the low latency alert pipeline that we are developing in CISA in Italy right now, and of course collaboration with Lorenzo as well as Enrico and Roberto Trota. Right, so of course the way I'm approaching this particular this problem is through machine learning, and perhaps by the end of this talk I'd be able to at least motivate you towards why that might be the direction to go if you want rapid alerts, or at least one of the directions that we must explore. Right. Okay, cool. But really quickly, I mean, just taking a step back, the Lisa data challenge is quite complex, obviously. And we have all these multitudes of sources and source classes, which all exist together at the same time. We've got these galactic binaries, which are extremely numerous, and we expect that to almost, but depending on what kind of sources you're looking at, it could populate and make it a little harder for those sources for our sources of interest to be inferred. And we also have these long-lived signals like MREs. However, the massive black hole binaries pose one unique challenge, which is the need for these rapid inference, because we want to be able to localize them in the sky before the merger happens, ideally, so that we can have a very rapid electromagnetic counterpart follow-up. And so usual methods that have gone towards coming up with rapid inference techniques tend to either look at very heavy sources, and that's for good measure, because heavier the source, the shorter the chirp. So the window of observation that we must make is quite small, and that makes it a little easier to train neural networks. And so the challenge going in on this project was to focus on a little bit lighter sources, something where the chirp mass ranges from 10 to the 5 to 10 to the 7. And so, well, it wasn't as trivial as that, but essentially those are the kinds of sources that we're trying to focus on right now. But before we get ahead of ourselves, I think I'd just like to reiterate why we need these low latency alerts and what kind of timescales we're talking about. So this is a famous, this is a paper by Marsad, Baker, and Rahul, where they look at how the source localization actually shrinks very, very, very close to the merger. So even about a few hours prior to merger, you end up having these 8 modes or 4 modes on the sky, and these modes result in very, very large sky patches, which is almost useless for electromagnetic counterpart, just because these are very, very large regions, and we're looking at telescopic observations. And so we expect refinement of the sky localization only a few minutes prior to the merger. And we need a method, therefore, that is able to provide updates on the inference of the sky position in the order of minutes or seconds as the data comes in. Of course, we're not quite sure how often we'll get the data chunks from Lisa, but that's another conversation to have. But we basically want a method that can provide as rapid as possible updates to our posteriors on the position in the sky. Right, and so one way that we can go forward, and the one that I'm focusing on, is a simulation-based inference technique. And very quickly, SBI is a way in which we can go from so we can go from data back to source parameters, and it essentially solves for the inverse problem. So as long as you're able to model the parameters that you want to infer, and you're able to simulate mock data from those parameters, we should be able to provide examples of data as well as these source parameters to a neural network, which is our simulation-based inference framework. And this neural network tries to invert that problem and provide a probabilistic inference of P of theta given data for that particular data segment at the time of production. So the idea is you spend a lot of time upfront training the neural network, and so this can be done offline, well before the launch of LISA. And once you have a network, we say that that particular network is amortized, meaning it can be at the time of production provide instantaneous, essentially, posterior inference, and we amortize the compute from the inference to the training. And so our paradigm follows something similar. We have an early and a late network. And so the early network has been trained offline well before the launch of LISA. And we've used a lot of compute. And this network would be able to provide a very rapid, quick, approximate posterior of the source. And the idea is to use this network hours in advance when we've already got a trigger, and we just want to get a rough idea of other source parameters like the chirp mass, the distance, and things that are not the sky localization, because we don't expect it to be very sharp at that time. And then once you localize in the parameter space this particular source, we can use that same network and fine-tune it for that particular source, right? And that involves using the same network and regenerating data within a few hours, training a whole network within that time. And therefore, we'll get more accurate sky localization from this fine-tuned network, or at least that's the idea here. And so I'll refer to these two networks as an SBI early and an SBI late. All right. And the way we train these networks, as you do with most machine learning pipelines, is through examples of data and the target label, or in this case, the parameter that we're trying to infer. And so as long as you're able to simulate multiple examples of this data, you summarize that data, you send it through a neural network, and then you repeatedly train this with a loss. The loss is basically guides the direction in which the weights and biases of the neural network have to be updated for you to get your objective, which is to get an accurate posterior. And then there's an additional step that most people do, which is like a form of calibration, but that's more of post-processing. Anyway, upon training this network, right, the main point of our method is to fine-tune that early SBI technique results. And so what it results, so what we do is a iterative zooming in method, wherein we first have, so I show you the loss evolution here, wherein initially we have the loss plateaus because the network is only able to go so far given a particular simulation budget. And then within the posterior that has been approximated by the network, we provide more simulations and we zoom in, and we zoom in until we reach a plateau in the loss. And all this takes about a few hours, depending on the number of GPU that you have and the compute available. But upon training such a network, as we get live data, as that enters our detector or as we're able to process them and provide it to our pipelines, where we can get instantaneous or nearly instantaneous posterior updates. So this is one example of a heavy source wherein very, very close to merger, we're getting we get these initial 4 modes in the sky, which slowly begin to disappear and finally converge. But you can see the method is not perfect. I mean, the ground truth shown in red here is a little off-center compared to where the maximum posterior is. And so there's definitely room for improvement. What we spit out, what the network spits out is not just a sky position, but almost the joint posterior. So we also get inferences on the chirp mass, which is the first column here, the mass ratio, the time of coalescence, distance, and the remaining parameters. And so an additional benefit of having such a method is it can be used as input to a offline analysis. This could, of course, be the global fit, but it could also be rapid refinement through MCMC after the merger. And that's something that we think about quite often wherein we hybridize this inference pipeline, wherein we don't just use machine learning and we don't just use MCMC, but a way in which we can marry the two and provide rapid but accurate inference. But I think very quickly, though, the caveats and assumptions we make here, I think, have to be highlighted. And these caveats do apply to most SBI techniques. We're only as good as our simulator. Therefore, we're only as good as the model specification. So we assume we have perfect knowledge of the possible waveforms that exist in the universe, and as well as the noise and modeling of other sources within the data. And so any mismatch would result in a potentially biased posterior, and that's something we have to keep in mind. Of course, this applies to even MCMC, because inside your likelihood are your model assumptions, but SBI is no different. Also, because of this particular the sources that we're looking at, the lower the masses, the larger the time window that we must observe, and the harder becomes the inference task, because you're going from a larger data complexity down to a small parameter complexity. And that makes it a little harder to train, which is why we're currently focusing on slightly heavier black holes, about 10 to the power of 5.7. And of course, we are assuming that we have an early detection pipeline, something that gives us an alert that there is a black hole coming into our data. We don't assume that we know exact inference on the chirp masses or the time of coalescence, but an approximate estimate does help us in training our network in that direction. And of course, for this preliminary analysis, we're assuming no contamination from other sources. So these are just MREs, and we're assuming there's just massive black hole binaries, and there aren't any MREs or galaxy binaries. Of course, one would have to include that in the final pipeline, and this would result in basically marginalizing over those source classes and source parameters. But yep, thank you very much. I think I'm right on time right now.
All right, thank you very much. Do we have any questions?
Hey Rahul, thanks for the talk. I have a question essentially about the timing. So you say that 5 hours, you have an early and a late network, and the late network has to be trained right before, well, in those couple of hours. And I'm thinking of two competing effects, and I wonder what your opinion is. One, that if you have a different SNR accumulation depending on the mass of the BBH, and that posterior that you get from the early network might result in a substantially longer than you think, I don't know, I'm asking, late network training. So do you think this is balanced as a whole, like it's a general recipe, or do you think this is very, very specific to the source that we've considered so far?
Okay, I think that's a good point here, and it's a little bit subtle, I'd say, the point, and so. Where is that? Yeah, right over here. Of course, keep in mind that the early SBI network, this can be essentially pre-trained, right, offline. And so the idea is it is as accurate as possible, right? Essentially an MCMC emulator. And of course, you're right, it depends on the source masses. So if the source is, for example, very, very heavy, about 5 hours prior to merger, it's not quite clear how sharp those posteriors are going to be. And so how informative would that be for our late time SBI is a point of question, which is also perhaps why we've chosen a sweet spot in the mass ranges. Now, if you don't want that, one thing we can do is parallelize it over multiple GPUs. So assuming we have a very, very high GPU budget, the training can scale linearly with that. And so we could potentially just make a lot more simulations and go through many epochs faster just because you have that much compute available. But that's definitely a important point to keep in mind. Also, one quick, something I forgot to mention is that from what I understand, the L2A, the low latency alerts, we still require them after the merger as well, because we still, so it's not just an hour before merger or just before merger that we need these inference techniques. So one can still continue to train these networks beyond that time and still provide inferences.
Okay, thank you.
Right, and I think we'll take one more quick question while the next speaker comes to set up.
I had a very quick question, whether your work is part of the DDPC broader work or if it's an independent pipeline.
No, the idea is to contribute to the DDPC, to the L2A division.
Fantastic.
I guess.
Thank you.
All right, let's thank Rahul again. All right, our next speaker is Sarah Burke-Spolaor, who's going to tell us about the BOBcat catalog.
Hello, everyone. This is a talk I'm not used to giving because I'm not used to talking about infrastructure, but a couple years ago I decided to propose to NSF to do such a thing. So here I am talking about it. And our catalog is called BOBcat, the Black Holes Orbiting Black Holes Catalog, and this is actually a catalog of candidate binary supermassive black holes. We have a fairly large team of undergrad and one high schooler contributions, but we are funded now. We have a web developer and a dedicated grad student and myself. So we are ready to go. I'm not going to do a big intro to the science because there was a huge introduction to the uncertainties in massive black hole emission this morning by a couple of people. But I do want to just point out that massive black hole binary science is severely intertwined in population analyses and observation of AGN and theory of AGN and black hole evolution, general relativity, gravitational waves. We all know this, that's why we're here in this session. But not only are all of those observations and theories important, but actually the parameters that we're observing in candidate binary black holes are quite important to understanding how they relate to the general populations, how these relate to whether we might detect them in LISA or pulsar timing arrays. And this is a really nice plot made by Dan D'Orazio and Maria Carisi, just showing a couple of different observing signatures of binary supermassive black holes and some candidates as they lay out in this, basically what I'm calling a binary model parameter space. So period, mass, separation, and a couple of other qualities. Here's a theoretical version of this, and you can read about it a little bit more in this paper we wrote in response to an Aspen meeting from last year. Dan D'Orazio made this. And the idea is that the theory here is also mapping a little bit to the way that you might expect to see different types of observing signatures. So this is all about the idea that in a certain region of parameter space, you would expect to see, based on relatively simple physical arguments, narrow accretion disks versus hot accretion flows, and evolving through this parameter space. So this is where we come in, and if I can remove Peter's face, you can see the rest of the text, but I guess I can't. That doesn't matter. So basically, BOBcat will be a catalog of binary massive black hole candidates. The idea is we want to link observers, theory, multi-messenger science, and we are limiting ourselves in BOBcat to include sources that are actually more or less binaries. These limits are a little bit practical, like we don't have a strict cutoff at 1 kiloparsec, but we don't want dual black holes, we don't want dual galaxies. These things are relatively easy to measure, and they are measured in different ways. But we're looking for separations 1 kiloparsec or less because we want binaries. The mass cutoff is also not really a hard line. Essentially, we want things formed through the merger channel, not things like emeries or stellar binaries. We are sourcing our catalog from peer-refereed manuscripts. And the idea is that there's lots of sources on archive. We might include those in the future, but at the moment, we want reliable parameters that aren't going to change with time as the refereeing process goes along. And we also, in the future, are planning some capabilities. But what I really wanted to do today was gather feedback from you all. We are at the point where we're about to release BOBcat publicly. We have a beta stage that we're going through. And as I'm going through this, I really want you to think about what you do and whether you could do it with BOBcat better. Is there something that we are not designing into our system that you would really like to see designed into our system? I wanted to talk a little bit about how we get the data into BOBcat. Essentially, it's just us reading papers. But this is really an exercise in homogenizing this very inhomogeneous set of literature. There is no ephemeris for AGN binaries because AGN are messy. binary black holes might have ephemerides, and that's kind of what I dream of making BOBcat into, is an ephemeris service where you could predict the evolution, but AGN do different things. So this is an example of a paper that was published recently. MRK 501 is the subject of it, where there's this radio observation, and there were two potential jets. One is being sort of lensed around the back, and there's maybe a Einstein ring that's formed, and you can look and see different periodicities in this data. One is 7 years, one is 121 days, one is 9 years. And then you could go and make a binary model out of this and assume a mass and eccentricity and predict some in-spiral timescales, et cetera. So there's a lot of parameters wrapped up in here in the observations and in the interpretation. So what we are doing is trying to pull published information about binary candidates and capture a little bit of the truth and the uncertainties in what is being observed. And it's a complex task, and we've spent a lot of time thinking about it. This is maybe a boring slide, but it's exciting to me because it defines our database and the information we are storing. If there's something you want stored or you would like to have access to, it should be in here, and you should tell us if it's not. I'll go through this a little bit. So the most basic thing is, of course, host information. Where's the object? What's its name? How far away is it? Redshift. You could play a little game of name that footprint. This looks a little like SDSS, and that's not a coincidence. A lot of these candidates are identified in large galaxy catalogs, of course. And you can see the pretty broad range of redshifts that these objects are spreading across. This is current BOBcat. We have about 1,000 sources in the catalog so far. We're still working our way through the full literature. Our binary model is really the meat of BOBcat. So anything provided and published in the paper, and then anything that we can calculate based on what is already published, we are sort of providing a value-added catalog to then calculate all of your mass parameters, or for instance, calculate the gravitational wave strain and in-spiral timescale based on some basic assumptions like circularity in orbit. We are also, that says error tracking. We're tracking the errors in these parameters, but we're also tracking the types of errors. So people say things like, look, we actually measured this, and it's a Gaussian plus or minus a sigma, as one does. There are also lots of papers that say, well, let's just pretend this has a mass of 10 to the 9 solar masses, and then calculate everything else in our system. So there's a little bit of quality control we are building into this catalog, such that if you want to really test a specific model with some future observation that you're planning, or whatever you're trying to do, you can filter out against these objects that don't necessarily have reliable information because it was some assumed value. We are also trying, I am a pulsar timing astronomer, I would say, and also a radio astronomer. We are trying to build in pulsar timing array interface directly into BOBcat, because a lot of these candidates, that's okay. Yeah, so here I'm showing just some sky maps of pulsar timing array data, and these are all continuous wave searches from the European Pulsar Timing Array, Nanograv in North America, Parkes Pulsar Timing Array, and the world, but it's the International Pulsar Timing Array that combines all those data sets and sets limits to say, out to some distance, we could detect a binary massive black hole of 10 to the 9 solar mass chirp mass. So we make these maps regularly, and they're stuck in a paper. So what we are trying hard to do now is gather the international timing array community to provide these maps and allow us to interface them with BOBcat such that we can do things like this. So this is the Nanograv map of the sky that's publicly available online. And all I've done is take BOBcat, overlay it, assume a seed black hole chirp mass for each system of 10 to the 9 solar mass, and say, well, which ones of these are detectable by pulsar timing arrays? You get out those green ones, and proceed with whatever science you want to do with that information. And this is kind of my axis, because I like to do continuous wave searches in pulsar timing. Of course, it's also a frequency-dependent phenomenon. So with BOBcat storing periodicity information, we might be able to do something slightly more complex than just overlay a map on the sky. Of course, we do hold the periodicity information. That's a critical part of a binary. Both orbital period, which is often modeled, and then sometimes just observed period, which like in the example of MRK 501, you could see there were multiple observed periods. We also tracked things like wavelength information. One of the other things that we are trying to capture is the evidence type and category and subcategories, such that if you're trying to design something like a survey, you could say, well, listen, I want to have all of the sources with continuum variability in the optical and go off and do a radio survey of them. This neatly combines all of the transliterature searches. It should be complete to everything. Within a year, we expect to be up to date to 2027, and be able to provide that information. I drew those pictures. I like them. We also are trying to build this into the classroom because as a public resource, I think there's a wonderful opportunity to allow people to use BOBcat in the classroom. And we're working with a team at WVU to say, build some rubrics that use these little extension project strings from which whenever I'm reading a paper, I say, oh man, I'd love for a student to do this or that. Or maybe like extend this model, assume something else about this parameterization. And then potentially have that student publish it in RNAAS and feed it back into BOBcat as a new model. So there could be a nice loop here, and if you're interested in doing something like that in your classroom, please reach out. Oh, this is a video. We are online, locally on my computer. WVU is working through security in our system, so this should be public and on actual online as of Thursday. So you can see our website is up and running. There should eventually be interactive plots to show your query on the sky with the gravitational wave parameters. Interactive little evidence tiles to show you cutely how, types of information you have. We have built this into I just forget the acronym, ADQL, so Astronomy Data Query Language. And you could go and search for your favorite, 1302 minus 102, and you say, whoa, wait a second. I didn't know it had those signatures, and look at the paper and go and read it. So there's a lot of interactivity we're trying to build into this to make these just an easy tool to help you explore binaries. Go off and I recorded this earlier, so I'm not controlling it now. But say you want to find all of the things within the pulsar timing band. So this is in years. I'm going to say, well, from a half year to about 10 years. Scroll all the way down, and there's your objects. Some interesting things you could look at. All right. Now, I want to know what your queries are. What do you want to do with this? Because we have the capability now and the funding to hire somebody to develop those capabilities. Or if you like coding, come and join us. I have a couple of projects I've been doing. One of my students recently was carrying out continuous wave searches on all of the jet precession binary models in the sky, and you can see some upper limits here drawn from pulsar timing arrays with the nanograv 15-year data. We've been working with that collaboration. My new student, Jordan O'Kelly, is also carrying out census, kind of studies with the binary black hole population and other similar studies. There's lots of things that we are thinking about doing. I have a catalog of post-merger galaxies, which have signatures. Look, I'm building a new mission. Are there any things I should consider designing it to be a little bit longer or higher cadence to observe all of these targets? There's all kinds of things that you might want to answer. Here's me in 30 years. I don't know how old I am. Thinking about this. Are there any binaries that might coalesce before I retire? Maybe in 2050 I need to write a proposal. Lots of things you could do. Theorists are something I really want to hear from, because I don't know how theorists think. They're amazing. But say you modeled a new theory, I don't know what kind of thing you would want to ask about that, but thing I might try to do and connect it to observation is say, are there existing candidates with the right parameters to actually test this type of source? It needs to produce radio emission. It needs to produce optical, oscillations. You might be able to find that, design new programs to observe it. Tell us. I've already said that a few times. So here is a giant QR code. Hopefully it works with that little thing in the corner. Point your phone at that. If you want to hear when BOBcat is released, or get on the beta testing team, get involved in education, paper extractions, code development, or just give us feedback, this forum will allow you to do all of that. I think I'm out of time, so I'm not going to go in detail through this timeline, but we have a lot of things still coming. Obviously, we first need to get online and let you guys try it out and use it. And we would love to gather any feedback we can from the community because this is for you, apart from also for us. Thank you.
All right, thank you. Any questions? Cool.
As more data become available from particular candidates, are you planning on updating these or removing some, for example? Because there are plenty of cases where more data just don't support the claim periodicity.
So we've debated, one of the things you see here is, I can't remember if I included it, but one of the things we were considering is how do we understand how to include refutations? And it's complicated and a lot of gray area because scientific debate is gray. The clearest examples are things like, there's NGC 3393 where somebody stacked up some Chandra data and just had an offset so it looks like a dual. So the data was processed wrong. So that probably shouldn't be in the list, and that's worth tracking. On the other hand, maybe somebody disagrees with the way the statistics were done, and then what do we do with that? So there's a lot of complexity in that type of question. Currently, our philosophy is just put it all in there, and people should read the papers in addition to using the catalog. If you're trying to go after 100 sources, one that's maybe not the right source is okay to leave in there. But if you have 10, you can probably read those papers and make sure you understand it. Yeah.
We'll do one more quick question. I think we're also going to go ahead and get the next speaker screen sharing.
In the BOBcat, will there be something like false alarm rate or something? Those kind of statistics?
So false alarm rate would imply a false alarm rate of that type. I guess it depends on your question you're asking.
So if you are using a particular observatory, how often noise can mimic a few periods?
I see. So presumably, because we're drawing this from foregone conclusions already analyzed in the literature, each of those analyses will have been different in terms of their false alarm probabilities and the techniques they used in the analysis, right? So presumably that will have already been done before presenting it as a candidate. Yeah.
Thank you.
Thanks, Sarah, again. I see we have our next remote speaker online. So Lazaros, if you could go ahead and share your screen. That works. Yes, I think that works. So let's go ahead and our next speaker is Lazaros Souvaitzis, and he will be telling us about misaligned circumbinary disks around massive black hole binaries.
Yeah, thank you. Hello, yes, I'm Lazaros, and I'm very sad that I couldn't be there in person, but I will just want to talk about some results from my ongoing project, which is practically in inclined SMBH binaries in circumbinary disks. And yeah, I think that I don't have to motivate the specific audience that much about the fact that we have numerous galaxies that they are interacting with each other and they form pairs. And given the fact that many of these galaxies will have a massive black hole in the center, then we form massive black hole binaries or pairs of massive black holes, if you want. So this is just from the JWST observations. And see, once the pair or the binary is formed, there are different phases of the evolution depending on the scales. For example, during the merger of the galaxy or towards the coalescence. But today, I'm gonna talk about this phase, this stage, which is practically the circumbinary disk phase, and we're talking about 1 to 10 of parsec scales. So yeah, I mean, once the binary gets bound, and since there's gas around, there's gonna be cavity created, and binary will accrete from the material around it, and it will evolve because of accretion and gravitational torques. This work has been, this type of systems have been studied quite a lot, especially the last 10 years, mostly through two-dimensional hydrodynamical simulations. And you can see, for example, here, the large parameter space in eccentricity and mass ratio. And although there is a zoo of results for out spiral versus in spiral, there seems to be a trend for the eccentricity, and that trend is practically around zero. There is an attractor around 0.5 eccentricity, and practically what it tells you is that more circular binaries will evolve towards 0.5, and highly eccentric ones, they will circularize down to this point. But I believe, and I think that it's important to take into account the full evolution in 3D. And this is what I do. I use moving mass hydrodynamics, AREPO. It's a simple, relatively simple setup, locally isothermal equation of state, fixed orbit, equal mass of the black holes, aspect ratio of 0.1, and we have a relatively large disk. It's extending up to 50 semi-major axis. Okay, this is very nice. This is the planar. You can see already the XZ projection of this, and you can see that there is a lot of things going on. But of course, an important parameter is the relative inclination between the binary and the disk. And there is no reason to believe that this is going to be forming in a coplanar configuration. And this is recent results from global simulations from Wang, Most, Hopkins, and others, which actually follow a galaxy merger all the way down to where the binary is to parsec or sub-parsec scales, and practically they find that there is a significant misalignment, which leads to the warping of the disk also. And this looks like that. For example, I have this exact same setup, but now I will tilt the binary 45 degrees, and you can see that the evolution is actually becoming really complex. And there is a lot of outflows. There is the continuous warping of the disk, which propagates outwards, and this affects, of course, evolution. So the first thing that we want to check is the evolution of the semi-major axis. Apart from the planar circular case, which seems to be expanding in line with the 2D results, all the other binaries seem to be shrinking. I have three eccentricities, 0, 0.3, 0.6, and just two inclinations, 0 and 45. Then we want to see the eccentricity evolution. Okay, the important part here or the different part here can be like for 0.3 eccentricity, which is different from what the 2D simulations find in the inclined case. So the planar case is more or less in line with the 2D simulations, but when we tilt the binary, not exactly. So the first take-home message already is that 3D effects will be important and will affect evolution, and this has direct implications because this can change the fraction of inspiraling binaries, and also the residual eccentricity that we'll get in the last phase, like the gravitational wave-driven phase. Also, we want to check where is the evolution of the binaries coming from. So practically you have this torque because of the gravity of the gas, and which part of the disk is driving the binary. And you can see this is radial. It shows the average radial torque, and you will see that in the upper panel there is not zero but small residual eccentricity coming from beyond the viscous radius. Viscous radius at around 500 orbits is what we expect for this system, so at which radius the disk has relaxed. And if you go to the inclined case, you see that these fractions are becoming much more significant. So the outer disk can have a big effect on how the binary evolves. And actually, this is the message I'm trying to say here, that having global disk simulations is crucial. We have accretion rates, very nice. You can see on top, like the modulation because of eccentricity. Once we incline the binary, you see there is additional modulation. For example, here, in the highly eccentric case, we have these phases of transient phases, which might be connected to disk tearing or breaking. I'm going to mention this in a while. But there's also a challenge of distinguishing if the modulation is coming from eccentricity or inclination, practically. So, because this would have direct implications for the optical variability we'll get. So my message here is that, yes, we can see this eccentricity modulation from which we can get periodicities and so on, but there's going to be a challenge probably for time domain surveys to have to distinguish between eccentric or inclined or both. We also measure how the relative angle between the disk and the binary is evolving, and the key point here is practically that circular binaries will tend to become coplanar with the disk, and highly eccentric binaries will become polar. You can ask me more about this. Is probably most likely due to Kozai-Lidov effects. And the final thing is that we have the warping of the disk, which can lead to disk breaking. Practically, you can imagine your disk as being a collection of homocentric annuli, and these are precessing, nodal precession. And practically, you compare the time scale of this precession to the communication between its ring, and if the latter is larger, then you have a potential break. So this is what I'm showing here. Again, for the three cases for the inclined binary. And you can see, for example, in the 0.6 eccentricity that after 100 orbits, we get this potential break, which also evolves as time is passing by, and the other cases can even develop this. Now, why this is important? Already many years ago, more than 10 years ago, this was proposed as a solution to the final parsec problem, which by now know that it's not necessarily a problem. And this is one implication, because this disk breaking can enhance accretion, and this might affect the stringing of the binary. And the second one, which is relatively new, is that recently there have been some simulations that they propose that this disk breaking can explain changing look AGN. So if you see on the bottom left, the three panels, they show the tearing of the disk, then the realignment, and then again about to break. And practically, if you then see the bottom right, the up right panel, the green lines are the three phases. So practically, they say that the luminosity, this phase will be seen in the luminosity. So I'm wondering if this can be also detected in binaries. This is something that I would actually be interested to look at. And the message here is practically this and the fact that we have polar alignment. I think I'm going to stop here, and I'm happy to take any questions, of course. Yeah.
All right, thanks very much. Do we have any questions? Anything from online?
Thanks for the nice talk. I was wondering, how do you motivate the initial conditions of these binaries being eccentric like 0.5, but still somehow in a steady state with the disk in an inclined manner? Can you hear me?
Yeah. So the motivation for the orbital configuration here is literally in a way to test against previous two-dimensional simulations. So we know that there is no good reason of the binary to be, I don't know, circular when after the galaxy merger or planar. And the values that I chose is practically to check, for example, this trend of the eccentricity. Do we go towards 0.5? And it seems that we don't in some of the cases. And for the inclination is practically, I'm just showing you here one extreme. I have more, and just that they're running, and I hope that there might be some connection regarding the eccentricity evolution, for example. Yeah.
Okay, because I understand the motivation for eccentricity as well as inclined disk, but I was wondering how do you put them together. But I understand it's more about exploration. Thank you.
Mm-hmm.
All right, let's thank Lazaros again. And if the next speaker could go ahead and come up. To our next speaker, Azeem Bari, who is going to tell us about eROSITA sources and the likelihood of them being LISA binaries.
Hello, everyone. My name is Azeem Bari. I am a PhD candidate at Vanderbilt University. I work with Dr. Malvina Bellotti on black holes and dwarf galaxies. However, today I'll be talking about using eROSITA to characterize the electromagnetic follow-up landscape of LISA massive black hole binaries. My collaborators on this project are Sophie Martinez-Fortis, Jesse Rono, and Karan Jani. So let's imagine we have this scenario where LISA detects these gravitational waves from inspiring black hole binaries. They alert the EM astronomers to look for this EM counterpart somewhere in the sky. And when we do that, we can do all of our fun, amazing, awesome multi-messenger astronomy. However, EM follow-up will rely on large sky error regions. So we have this plot here from Mondrielli et al. 2020. And delta omega on the y-axis is the sky position uncertainty, and on the x-axis is the time to coalescence. And so even one day before merger, a binary with a total mass of 3 × 10⁶ solar masses and a redshift of 1 will have a sky position uncertainty of around 1 square degree, which is a pretty large volume still. And so estimates of EM counterparts in a LISA error volume range anywhere from 10⁻² to 10⁵ potential hosts inside of an error volume. This was shown by Lopes et al. 2022. And as you can see, a visualization of that in the plot at the bottom. However, when we introduce and think about X-rays, if we only consider the host galaxy to have an X-ray AGN for an EM counterpart, this number is reduced significantly to anywhere between 10 to 10⁴ potential hosts that have X-ray AGN. And this can be seen in this plot on the right from Lopes et al. 2022. And these masses of these numbers range depending on the mass, the redshift, and the time to coalescence. So using X-rays significantly reduces the number of potential hosts. And just to give kind of an overview of how these X-rays are made, there's a couple examples. In a single black hole case, we think of them as we have like an accretion disk, and the accretion disk emits photons in the optical and UV. And those photons, some of them go through what we call the corona, which is a cloud of hot electrons, and those photons get Compton upscattered into the X-ray. And in the binary black hole case, in one instance, you can have thermalized X-rays from the simulation from Tang, Hyman, and McFadden. And the thermalized X-rays come from the mini disks, the cavity wall, or even the outer disks. So all this is great, and these models are fantastic. But another challenge will be that LISA will detect massive black hole binaries in dwarf galaxies. So we can see in this plot here on the left from Kolpe et al. 2019, LISA will have high cyclic noise for black hole binaries in the range of 10⁴ to 10⁷ solar masses. And if you look in the plot on the right, this black hole stellar mass relation from Ryan's involuntary 2015 If we define a dwarf galaxy to have a stellar mass anywhere between 10 to the 7 to 10 to the 9.5 solar masses, they will harbor a host galaxy, they will harbor a black hole in their center anywhere between 10 to the 4 to 10 to the 7 solar masses, which is right where LISA's peak SNR is at. And finding black holes in dwarfs is a challenge. Black holes in dwarfs are smaller and therefore less luminous. The AGN signal can be hidden by star formation, and this overall makes isolating the black hole from the host pretty difficult. And we cannot perform our typical luminosity cuts that we are used to using on these brighter quasar in AGN. And this is because there's a lot of confusion in this X-ray luminosity regime where we're not as bright, and we can, like objects like X-ray binaries and other stellar phenomena can produce luminosity similar to dwarf AGN. So the big questions I want to answer today are, what can existing surveys tell us about the LISA EM follow-up landscape? And can we do this with X-ray emission alone? So in order to do this, we use eROSITA and SDSS to determine what the X-ray sky looks like in the region of parameter space occupied by LISA massive black hole binaries. So some overview, what is eROSITA? eROSITA is the extended Röntgen survey with an imaging telescope array. It surveys the entire sky at approximately uniform depth in the 0.2 to 10 keV range. Overall, it's an improvement on the completeness and homogeneity of other X-ray catalogs out there currently. And the two main catalogs that eROSITA gives us are eFEDS and eRAS-1. So eFEDS, or the eROSITA Final Equatorial Depth Survey, observe this field right here in particular to demonstrate the capabilities of eROSITA during its performance verification phase. And this was during November of 2019, so this is a pretty recent observation. And the flux limit of the eFEDS survey is 6.5 10 to the minus 15 ergs per second per centimeter squared. This will be relevant in just a second. And the overall eFEDS catalog hosts about 28,000 or so sources. Now for eRAS-1, or eROSITA All Sky Survey first data release, observed the entire sky in the X-ray from December 2019 to June 2020, although only the western half of the sky is publicly available to us. The flux limit of eRAS-1 is 5 10 to the minus 14 erg per second per centimeter squared, so not quite as deep as eFEDS goes. Overall, though, it has the same detection method as eFEDS. And the overall eRAS-1 catalog has almost 1 million sources, so quite a bit more compared to the 28,000 from the eFEDS. And finally, the other catalog that we use comes from the Sloan Digital Sky Survey, DR18, or SDSS. SDSS provides optical counterparts to eFEDS, which gives us reliable redshifts and classifications for about 13,000 eFEDS sources. So roughly half of the eFEDS catalog has reliable redshifts and classifications. And these classifications being QSOs, which are basically quasar and quasar-like objects like AGN, galaxies, and stars. So to give a quick summary of the catalogs used here, some of this got a little messed up, but that's okay. We have the eFEDS plus SDSS catalog, which gives us X-ray flux and optical spectra, redshifts, classifications, and overall the eFEDS X-ray survey is deep but a small field. While on the other hand, eRAS-1 gives us X-ray flux, but we don't have any information about redshift or classifications. And even though it's a shallow field, it's a wide field. So what we want to do ultimately is we want to learn source properties from eFEDS and transfer that data and apply it to the larger eRAS-1 sample. So to do this, we first compare the, in order to compare the surveys fairly, we first match them to the eRAS-1 flux limit, and this forces the eRAS-1 and eFEDS catalogs to have the same depth. And doing that allows us to draw conclusions about the larger eRAS-1 sample using properties only available to us in eFEDS. So we have this plot here on the right where we have a histogram, and we have log flux on the x-axis in the soft band, and the gray is the eFEDS, the normal eFEDS samples flux distribution The black is eFED's flux limited distribution, and the blue is the ERAS-1 flux limited distribution. So lots of acronyms, but as you can see, these two distributions are roughly the same. They're not exactly the same, but it's good enough for the type of analysis that we're doing. So ultimately, we want a mass redshift distribution like the one we see here from Kolpe et al. 2019, but we want to see how this looks for the ERAS-1 sources. So we project ERAS-1 fluxes onto the LISA mass redshift space to see if they occupy the same regions of parameter space. And so in order to do that, we have to convert the 1D flux into a 2D mass redshift space. So how do we do that? So first, let's tackle the redshift. So as I mentioned, the ERAS-1 sample has no redshift information. But we do know that a source is not equally likely to exist at all redshifts. So our X-ray telescopes are only going to be able to see sources. It's more likely to see a source at redshifts 1, 2, or 3 from our selection bias compared to like a source like at redshift 10 or 15. So we use eFEDs to constrain the most probable redshifts for the ERAS-1 sources. So in order to do that, first we make this flux redshift distribution for eFED's QSOs. We then model the flux redshift probability distribution using a Gaussian mixture model. And then for each ERAS-1 source, it is assigned a redshift probability distribution conditioned on its observed X-ray flux. So each ERAS-1 source has a redshift distribution and a probability distribution associated with that redshift. Now, in order to constrain the mass, we have X-ray flux, and we assume a photon index of 1.8, a bolometric correction of 16.7, and an accretion at the Eddington limit. This is for the most optimistic scenario. And if we do this over an entire redshift grid, we end up getting this equation here. It's a very crude estimation, but it works for what we need to do. And we end up getting a mass distribution as well. So here's an example of this one particular object. We have an input X-ray flux of 8.3 times 10 to the minus 13. And we have this mass distribution from our redshift grid from earlier, and associated with that, we have a probability distribution from earlier as well. Now, if we do this for every single source in ERAS, we end up summing the probabilities in each of the mass redshift bins, and we end up making a overall 2D histogram of the entire ERAS-1 mass redshift distribution. So we can see that here in this plot, where we have redshift on the y-axis and mass on the x-axis, and the probability distribution where the higher probability is in the darker colors. And we have solid lines of LISA SNR overplotted. And as you can see, if you assume that the source is an AGN, X-ray surveys with eROSITA-like sensitivity will indeed detect sources with fluxes consistent with the mass redshift space of LISA massive black hole binaries. But we still have this one remaining question: can we do this with X-ray emission alone? So as we mentioned earlier, we can't just use X-ray luminosity cutoffs in dwarf galaxies. So we need a way to differentiate between whether we're looking at a central black hole or merging black holes, or if we're looking at stellar processes like an X-ray binary or a magnetically active star. So to do that, we use optical spectroscopy. So here's some examples of spectrum of a QSO, of a galaxy and a star. And what we see is we have 78.3% of our sources were classified as quasars, 8.4% were galaxies, and around 13% were stars. So even though 13% is not a huge number, the significant stellar contamination in X-ray selected samples demonstrates that spectroscopy will be a critical component of LISA EM follow-up campaigns. And here is my summary slide, and thank you for listening.
All right, thank you very much. Do we have a question? Yes, Tamara.
for your talk. I just wanted to ask, you're converting X-ray fluxes into potential masses of compact objects. Do you have to assume some kind of volumetric correction for the X-rays? And do you have to assume the Eddington luminosity fraction? And what did you assume about it?
Yes, so we assumed the volumetric correction of 16.7, which is from Durres et al. 2020. And this is for, in particular, like black holes and AGN in the mass range of 10 to the 5 to 10 to the 7 solar masses. And we assume accretion at the Eddington limit just in order to get the most conservative masses, because if you accrete at the Eddington limit, you're going to get as the smallest masses. If you accrete below Eddington, your masses are going to be larger.
All right, and let's have the next speaker go ahead and come up while Jeremy asks this question.
Is there variability information in either of those surveys?
I don't think it's publicly available yet, but eROSITA will be a time domain survey. So when the future data releases come out, we can look at variability and make X-ray light curves.
All right, let's thank Azeem again. All right, our next speaker is Ananthu Lali, who will be telling us about the role of observation duration and EM priors in constraining gravitational wave parameters with LISA.
Good afternoon. My name is Ananthu Kedali, and I am a PhD student from University of Alabama in Huntsville. And my presentation is on evaluating the role of observation duration. Observation duration and EM priors in constraining gravitational wave parameters with LISA. So for a brief overview, so what are UCBs? UCBs are prime double wide dwarf systems with orbital periods below 1 hour. We have a small subset of them which are called non-binaries because they are already observed electromagnetically. They are historically thought to serve as benchmarks for testing LISA's performance, since they produce gravitational waves observable in LISA's millihertz band. In 2024, we show that these non-binaries may not be ideal candidates for evaluating LISA's performance, as they reside in the densely populated regions of the spectrum, because these signals are overlapping. So if you try to do a blind search for them, you won't be able to recover those parameters exactly because of these overlapping sources. So there are a few challenges with UCBs. For most of these UCBs, if you look at the observation time, you can see that the frequency evolution is so small to constrain FDAT, which means that the FDAT will be weakly constrained, which also means that the chirp mass will also be weakly constrained. There are also a few systems, like for instance M-conven, which have mass transferring effects as well as tidal effects. And so if you do the conventional way of doing inference, you will be ignoring these effects, so which will also bias our inference. So in order to account for these effects, you would need distance, amplitude, and inclination, all that. But if you do a gravitational wave only inference, you won't be able to constrain the distance and amplitude inclination because they are degenerate. So these challenges motivates us to use a multi-messenger approach where we can combine both the EM observables with the gravitational wave observables. And we see the frequencies, FDAR, sky location, and all those list of parameters which we infer from electromagnetic as well as gravitational wave observations. The frequency and sky location and the distance are constrained better by EM observations. The amplitude alone is constrained only by the gravitational wave observations, and the inclination is constrained by both EM and gravitational wave observations. And these two equations are the one that we use in our project, and I will explain what we did with that in the next slide. So First, we started with the LDSoft, which is a library of tools which actually gives us the VBM-CMC sampler. VBM-CMC sampler is a specific type of sampler which is used to analyze the verification binaries, and it uses parallel tempered MCMC. So we first fixed so we run this MCMC by fixing the frequency and sky location, because we already know the information about that from EM observations, and it gives us the samples on amplitude, frequency, inclination, polarization, and phase. We also have the information of the distance and its uncertainty from Gaia, and we use that to draw normally distributed samples, and we combine that with amplitude samples that we got from the sampler to get the mass samples. From there, we can fold that into that equation there and to like a constraint for f.gr, and from f.gr you can get the value for f.astro from the previous equation here. And from there, and then we use inclination cuts, which we obtain from a table, which I'll explain later. And so after the inclination cuts, then we have two set of samples right now, which has the inclination cuts and which don't have inclination cuts, and we then convert that to P and P dot and all that. So we ran the analysis for 11 binaries. This is the M-conven, and you can see the green distribution is the uniform distribution on chirp mass, and the blue distribution is the distribution for the chirp mass that we get only by Gaia and the amplitude. And when you apply the inclination constraint, it gets even better. And if you look at the right plot, which is the P dot astro, you can see that the effect of the inclination cuts are very marginal, and I'll explain why that's the case in the next slide. In the P dot gr, you can see here that which is the blue distribution, the Gaia plus the amplitude is already well constrained, and when you apply the inclination cuts, it gets better here. And the reason for this is because P dot gr is proportional to the chirp mass, which is proportional to the amplitude, which is strongly correlated with inclination. So once once the P dot gr is strongly constrained, then the remaining uncertainty in the P dot astro is dominated by the uncertainty from the P dot, and the P dot is weakly correlated with the inclination. So that is the reason why the inclination cuts on the P dot astro isn't making as much of an effect here. And so we ran this analysis for in total of 11 binaries, and this is for a 4-year observation time. And as you can see here, so the takeaway from this plot is that if you look at the chirp mass, you can see that the blue distribution, which is the Gaia plus amplitude, it's already well constrained for most of the sources, which is like two sources which we see a moderate shrink of the full width at half max, and for 6 of the sources we see a significant percentage shrink. So in total of 8 sources we see a moderate to significant shrink, we see that, but the effect of the inclination isn't as much of an effect for the P dot astro. So that is the takeaway from this plot. We also ran it for a 10-year observation time, and the story here is quite a little bit different, because after a long observation time, most of the improvement is coming from that long observation time, and it improves the SNR. And after the long period of observation, there is very little room for improvement for the inclination cuts. So we don't see as much of an effect as we see with the 4-year case. So in total, we see 6 sources which see moderate to significant percentage shrink. As usual, we don't see the effect of the inclination for the P dot astro. We also had a situation where two authors were reporting two different values for the chirp mass based on their evolutionary model assumptions. Their mass ranges were also kind of overlapping based on the 2 sigma technical range. So we ran the analysis on them, and so what we see here is that so the posterior distributions are actually kind of well separated. So although there's a small kind of overlap there, we can see that it's actually kind of well separated. And when you apply the inclination constraints, it's even well separated. So what this means is that when LISA goes operational, it will be able to tell them apart. So that's the main conclusion from here. So to talk a little bit about my future work, so this is the table actually I kind of used for my inclination cuts. From the inclination column, you can see that most of the values are inconsistently reported here for the uncertainties. Some of them are in square brackets, some of them are uniform, some of them are Gaussian. So for this project, I used those values and I used them. I converted them into a uniform ones, and I used those kind of uniform on those as inclination cuts. And but for my future work, or the work which I'm actually almost done, so I taught the sampler to parse each one of them. So if it sees a Gaussian prior, or if it sees a uniform prior, it could use that like a prior distribution during the sampling process itself and do the inference as well. So that was an improvement I made for the work which I almost like wrapped up. And in the future, I'm also working on the mass as well. For the mass case, it's slightly different here because the mass one is more kind of inconsistent here. So the mass correlations are also absent here. So the best conservative approach was to use a uniform. So I took the extreme values and I calculated the mass ranges, and I applied a uniform prior on those chirp mass, and I used a uniform prior on that. So that was the best conservative approach to do that. And in the future, I also plan to use a joint inference of all these, so that it takes into account of the correlations and all those EM plus as well as those gravitational wave observations as well. So with that, I conclude.
All right, thank you. Do we have any questions?
Thank you so much. You were very convincing in telling us that we should constrain the inclinations for these binaries. Can you quantify, like, how well do you need to know the inclination such that the effect is visible? Like, is it like 5 degrees, 10 degrees, or 1 degree, half degree, something?
I don't understand the question. Can you repeat once again?
So how well would you like to know the inclination such that it has a visible effect on the chirp mass constraint, for instance?
Oh, so we used the percentage shrink. So we defined moderate and as well as kind of significant based on So if the percentage shrink in the full width at half max, if it's between 20 to 60%, we define that as moderate, and if it's more than 60%, we define it as significant. So that's how we do it. Yeah.
All right, let's think Ananthu again. And our final speaker of this session will be Malvina Bellotti. We'll get her pulled up. Malvina Bellotti will be telling us about massive black hole binary parameter estimation with conditional flow matching.
Thank you. Thank you for the introduction. So hello, I'm Malvina Bellotti, and I'm a first-year PhD student at the Observatoire de la Côte d'Azur in Nice, under the supervision of Natalia Korsakova and Jess McIver. Today, I will talk about massive black hole binary parameter estimation, employing simulation-based inference, and specifically conditional flow matching. Sorry. Maybe. No. Oh, okay, I can click. Okay, sorry. So let's start from our systems, so massive black hole binaries, and so you've heard about them today and yesterday as well. And so massive black holes are found at the center.
Sorry, they're talking about the problem. What's the problem?
It's stuck on the...
It's stuck on the first slide.
Oh, okay, sorry, I clicked, maybe I...
No, I don't think we do. It's finicky. Still no? Okay. So we're going to stop sharing, and we're going to try again.
Yeah, no
Sincerely
problem.
apologize.
No problem at all.
Okay. Desktop, maybe that will do. Oh, now.
Yeah.
Okay, perfect. Okay, so now also the arrows work. I was saying massive black holes, you've heard about them. They're at the center of most galaxies, and since the galaxies merge, we expect them to form binary systems as well. They will enter the LISA band days months before the merger, and they will be, as you can see here, the loudest sources that LISA will be able to see. If they merge in environments with a sufficient amount of gas, then we might be able to observe also an electromagnetic signature. And this is why I'm showing here also the time to merger, because we might, if we provide a measurement of the distance through gravitational waves and are able to detect the same system through electromagnetically, we might have a measurement of the redshift as well and might be able to constrain cosmological parameters. This specifically needs to be done in a specific pipeline, because the main data analysis pipeline that is going to be employed for LISA, as you all know, it's the global feed that will perform inference on all of the sources at the same time, and will therefore will be too slow to perform inference in real time. As I was saying, so a dedicated pipeline will be needed to both trigger multi-messenger alerts and provide probe parameter estimates to the electromagnetic community, but also to trigger protected periods in the data stream, so that if we know the merger time, we might not have scheduled gaps during the merger. Moreover, such pipeline can provide some starting point to complete parameter estimation pipelines. The goal will be to analyze signals in less than 30 minutes from when data reaches the ground, and we will need to be able to update the parameters continuously. We've heard differently this morning, but my main focus is on massive black hole binaries, and but I want to stress the fact that we will need to perform the analysis in presence of other sources as well, and in presence of noise, realistic noise, gaps, glitches. Okay. A powerful tool that we might employ in this context is simulation-based inference. You've heard it from Rahul already. In fact, I'd say there are two main reasons why this is particularly powerful. First, we don't need to write down a likelihood. So in the case of multiple sources, non-Gaussianities, non-stationarities, it might be difficult to write a likelihood, right? So with simulation-based inference, we are sampling the training data set we sample from the parameters priors, we add noise and whatever we want to add, put it in the training set, and we sample from the joint distribution effectively. we train a neural network that should be able to learn the posterior distribution. The other important point for which simulation-based inference might prove useful is that, as Rahul was saying, it's amortized inference. So we train, and we might take a long time to train our network, but then the inference is running seconds. So well within the low latency requirements. Okay. In our case specifically, we're using conditional flow matching. It's slightly different from what I've just told you. We don't really learn the posterior distribution, but we learn the mapping between a easy-to-sample distribution that could be a Gaussian, and we learn a velocity vector field, so basically the mapping that to map the prior to the easy-to-sample distribution to our actual posterior. We use optimal transform to do so. It's just easier to train if we force the paths to be straight. And so the objective changes a bit. We don't really learn, we don't really compare the posteriors that we get, but we learn the mapping, and we can use a mean squared error loss. Okay, so specifically in my case, for the massive black hole binary, I'm focusing on astrophysically motivated prior. So I sample my prior from a population of massive black hole binary that I expect to emit electromagnetically as well. So here you see we took these populations from Manjali et al. And in blue you see the total massive black hole binary population, while in green and red you see the multi-messenger candidates. So yeah, for now we're focusing on these smaller priors, but we might be able to make them bigger at some point. Okay, so yeah, so what I do, I get these set of priors on the parameters, and I sample from them. This is just an example of the 3 populations that I sample from. Okay, then I produce my data. I simulate my waveforms, and I do so. So for now, we're using waveforms that are employed in Sangria. So BBHX for massive black hole binaries, and so phenom-HM waveforms, and using BBHX. I'll tell you later why, but also I'm producing galactic binaries with GPU. We will be moving towards Moito-based waveforms, so time domain waveforms with a full response, the ones that are going to be employed in Erebor as well. Okay, so our network will be able to ingest 2 different representations, so both time series and time frequency. No, is already able to do so. Time series, we produce data on the fly, and so the training might be slower, but we continuously produce new data as we train. While in the time frequency, for the time frequency representation, I produce a data set offline. This is motivated by the fact that, well, it might be easier for our network to learn patterns in an image. So we're exploring this time frequency as well. And both time and time frequency will allow us to insert gaps, glitches easily. Okay, I've explored the different time frequency representations, and still it's in the works, checking whether how they affect the parameter estimation. So produce several, and we see if and how they affect it. The easiest short time Fourier transform, but we explore scattering transform, which is basically a convolutional neural network with fixed weights, but also synchronous squeezed wavelets and superlets, and different types of Q transforms as well. So we see how they're affected. Okay, a quick proof of concept. So what we are gonna be doing is we will need to marginalize over the signals that we don't care about. And so what I tried to do, what I did, is train some autoencoders. And this is just I've just added a couple of galactic binaries, and of course it will be done at scale, right? But what I do is I compare an image with some spurious sources that I don't really care about, let's say, and I compare it to an image without them, and then I ask the network to learn how to cancel them out. These also will need to be tested, so I still have to check whether it affects the parameter estimation, like the presence of galactic binaries. I might just add the signal with the galactic binaries in the training, and the network might be able to marginalize on its own. But yeah, for now, this is just what I'm doing now. At the moment, I'm just training on the massive black hole binaries, still not with other sources inside. Okay, so these are very, very preliminary results, but so our network is able to run both on time and on time frequency. Yeah, we're still in the debugging stage, but what I wanted to point out is that the network, well, we have to compare to standard MCMCs, so to be able to compare the posteriors and see how good we are doing, or how well we're doing. But what might be interesting is that the network, in this case at time frequency, is able to learn the structures that, well, the parameters that define the shape of the signal, but might not be able to reconstruct the scale acquisition as well. Yeah, perfect. So yes, as you can see here, some diagnostic plot, just to see that it doesn't really converge pretty well, but yeah, it's in the works. And a quick slide on the fact that we decided to call this Seldwin, which means a flowing river, and it's the river that flows down from the Erebor mountain, Erebor's global feed pipeline. And also because, as I was saying before, this pipeline could provide some initial guesses and some starting point to the global feed, and to improve convergence of it. And it will run in the presence of multiple sources as well, marginalizing them out. So, to summarize, simulation-based inference could prove useful for low latency parameter estimation, both because we don't need to write down a likelihood, and we can run inference in seconds. Simulation-based inference, our network can marginalize over will be able to marginalize over other signals, artifacts, and non-stationarities. We use both time and time frequency domain. Time frequency representations might better align with our architecture, but what we need to do is to actually compare with MCMCs to use some time domain waveforms and investigate the monitor dataset as well. And then we need to actually add other signals, realistic noise, glitches, and gaps in our dataset. That's it.
All right, thank you. Are there questions for Malvina? Yes, please.
I think under.
Okay, I have 100 questions.
Yeah.
I'll just ask like 2. Among your next steps, since you're talking about this as part of a low latency pipeline, do you plan on training this whole infrastructure just on in-spiral signals?
Yeah. For now, I'm training on the whole signal, but we will have to cut them.
Okay.
Yeah.
And then my other question is about the cost of the training and how often you have to retrain as the noise level changes, especially in the first couple of years. I'm not thinking about non-stationary instrument noise. I'm thinking about the dramatically reduced foreground as we integrate longer. Yeah.
So I haven't explored that yet, and yeah, I'm not sure. Meaning that I haven't explored. The training doesn't take too long. It takes 3-4 hours, I guess, for now. Yeah, but I'm training on not too big of a data set as well. But I guess yes, when we will need to think about the level of the noise and how it changes because of the galactic foreground. Yeah, I guess we'll be able to receive some level of the noise from the global feed and able to retrain, I guess, as we go on.
We have time for one last quick question.
Sorry, very quick question.
So when you subtract MBHBs to decrease the cost of global fit, if these MBHBs are affected by some astrophysical noise like eccentricity or gas imprints or other things, how difficult it will be to include a few other parameters in the MBHB inference pipeline, and how much it will increase the cost?
Okay. Well, okay. So for now we run inference on a specific set of parameters, but I guess one could add inference on other ones. So then retrain the network, though. And yeah, I guess it's one of the next steps, right? To be able to add additional sources of noise, and we might want to infer some of that. I guess what we will try to do is try to marginalize it, right? So to be able to ignore some sources of noise, and also the priors will be broad, just to serve as initial points, and then the global field will do the subtraction, and we'll care about all of the problems that are connected to the subtraction of the signal, I guess. Okay.
All right, well, let's thank Malvina and all of our speakers. And thanks to all of you for your patience with the tech issues.
Recording stopped.